Okay, welcome back. Now we're going to take a look at the next section, 9.2, which is working some more with the radicals. I'm going to ask you a question first. Do you think the square root of a plus the square root of b is equal to the square root of a plus b, and why or why not? Go ahead and pause the video and think about that for a minute. Another way that we can we could try and disprove this like we did yesterday. Do you remember how we saw that the square root of a squared plus b squared is not equal to a plus b? We proved that by example. We could do the same thing here. Let's make it easy on ourselves. Let's choose two perfect squares. How about let's let a be 4 and b be 9. And we're wondering, is this equal to the square root of 4 plus 9? Well, the square root of 4 plus 9 we know by the order of operations is the square root of 13. This is not a perfect square. That would be an irrational number. But on the left side, the square root of 4 is 2, and the square root of 9 is 3. 2 plus 3 is equal to 5. Is 5 equal to the square root of 13? No. So we know that this is not true. It's not true. And a thing to remember is when you have pluses and minuses with radicals, we just have a really tricky time putting them together. Well, let's take a look at another example. What about if we multiply? Do you think the square root of a times b is equal to the square root of a times b? Well, you can pause and think about it, try a couple numbers, or let's just follow the same kind of method we used before. Let's let a be 4, so we would have the square root of 4, and let's let b be 9. Those are just random numbers that are easy to work with. Do you think this is equal to the square root of 4 times 9? Well, let's go ahead and do the math here. The square root of 4 is 2, and the square root of 9 is 3, and 4 times 9 is 36. 2 times 3 is 6, and the square root of 36 is 6. So we proved that it is true for any two random numbers. And in elementary math, which is what we're doing here, if you can do that, choose any two random numbers and it works, odds are that it's always true. So actually, this is always true. When you multiply two radicals, you can just combine your numbers. What does this mean? This means that the square root of 2 times the square root of 3 can be simplified to the square root of 6. And vice versa. The square root of 12 can become the square root of 4 times the square root of 3. We can break them apart by factoring. These are true statements. Not true for adding, but true for multiplying. And this is exactly the technique that we are going to use to simplify radicals. I don't think you've seen this. This is one of the trickiest things that we learn about radicals. This is a skill that you will use right through high school in science and in your higher classes, math classes. Okay, so there are a couple of methods, a couple of ways that we can go about simplifying a radical. First, what does that mean to simplify a radical? That just means, like, if you had the square root of some large number, there is a way that you can make the number under the radical sign, which is called the radicand, make that as small as possible. How do we do that? We want to factor this number into factors that are perfect squares. What are the perfect squares? We wrote them down last time: 4, 9, 16, 25, etc. Now when we look at 40, we can factor 40 in a bunch of ways. We could go 40 times 1, 20 times 2, 8 times 5. None of those factors are perfect squares. So the way that we're going to choose to factor 40 is into 4 times 10. Why that? Because 4 is a perfect square root. 4 is a perfect square, so you can take the square root of it. The square root of 4 is 2, and this becomes 2 square roots of 10. This is simplified. It is in fact equal to the square root of 40. And hopefully you can see how the simplified version is just going to be easier to work with in the future. The radicand is as small as it can go. How do I know that? Well, what are the factors of 10? 10 and 1 or 5 and 2? None of those are perfect squares, so we've got this as low as it can possibly go. All right, the more you do these, the easier they become. The square root of 8. Factor this into numbers, hopefully that are perfect squares. So perfect square, 4. 4 is a factor of 8. So we write this as the square root of 4 times the square root of 2. And then we simplify. The square root of 4 is 2. The square root of 2 cannot be simplified. So the square root of 8 becomes 2 square roots of 2. The square root of 75. What is a factor of 75 that is in that list of perfect square roots? If you wrote those out on a card, you might want to take a look at those. When you do, you'll recognize that 25 is a perfect square. It's a factor of 75. 75 equals 25 times 3. And the square root of 25 is 5. So the square root of 75 becomes 5 square root 3. It's at this point in time that I would ask for questions, because I'm sure there's got to be some. But in this format, unfortunately, it's hard to do that. If you do have questions, go to the classroom stream and ask them there. And your classmates can help you, and I can help you too. We already did the square root of 12. That became, we didn't do the square root of 12. We did factor it up here. Square root of 4 times square root of 3. Square root of 4 is 2 square roots of 3. So the most often question I will get from students is, why not square root of 6 and square root of 2? Let me use a different color pen for that. What if we wrote 12 as the square root of 6 times the square root of 2? This is true, but this doesn't get us anything because neither 6 nor 2 are perfect squares where we can simplify. That's why we don't choose those factors. We do choose these factors of 12 because the square root of 4 is 2. Okay, it gets to be a little bit trickier as your numbers get larger. 180, wow. I see that 18 and I recognize a factor of 9. 9 is a perfect square. So I could write this as the square root of 9. 9 goes into 18 20 times. So we have the square root of 9 times the square root of 20. The square root of 9 is 3. So this becomes 3 square roots of 20. Now, just like when you're simplifying a fraction, like if you had 6 over 12 and you said, oh, if I divide both by 2, that would be 3 over 6. You know, you're not done. You could still take this down into 1/2. That's what happens here. The square root of 20, you should ask yourself, does 20 have any factors that are perfect squares? Yes, indeed. 20 is equal to 4 times 5. This 3 is just going to come down. He stays outside of the radical. The square root of 4 is 2. Guess what's going on with that 3 and that 2? They're being multiplied. So the square root of 180 becomes 6 square roots of 5. We did all of that without grabbing our calculator, and all of this work I expect you to do without using your calculator. Now, if we had recognized, you see this 6? we could have recognized that 180 is divisible by 36. It's equal to 36 times 5. 36 times 5. And then you could have gotten that. But this is something that I did not see. I did recognize the 9 here. Lots of different ways that you can break that down. It's almost like a factor tree. Okay, we're going to move on to simplifying this kind of an expression. Now we've got variables. Well, we can take the square root of a squared. That would be a, but we can't take the square root of b. We have to leave the b under the radical. Remember from what we just learned that the square root of 50a squared b is the same as the square root of 50 times the square root of a squared times the square root of b. And we're going to try to simplify all that we can. So square root, perfect square factors of 50, numbers that are perfect squares and factors of 50. So that's 25 and 2. I don't have to rewrite those. The square root of 25 is 5. The square root of 2 is so small we can't do anything with it. The square root of a squared, we can simplify that. But the square root of b, we don't have enough b's underneath there to take any out, so it just remains the square root of b. Now what we want to do is we can multiply the regular coefficients, regular meaning they're not under the radical, multiply those together, so this should be written as 5a. And then now we multiply all the numbers under the radical, 2 times b, 2b. So our final answer would be 5a times the square root of 2b. Simplified. I would suggest that you pause the video and see if you can do this one on your own. The square root of 48x squared. So 48 actually has a factor of 16 and 3. You might have wanted to take the 4 out, that's fine, but when you get down you have to take another 4 out. The square root of 16 is 4. The square root of x squared is x, and then we have the square root of 3. This is what you should eventually have, 4x times the square root of 3. We have one more concept to look at. It's our last question. Do you think that the square root of a over b is equal to the square root of a over the square root of b? Why or why not? Well, let's use our handy dandy numbers for a and b again, shall we? So this is going to be a little bit trickier to show, but if you had the square root of 4 over 9, this can in fact be equal to the square root of 4 over the square root of 9. Just like multiplication, in division you can break up the parts of your radical. And the square root of 4 is 2, and the square root of 9 is 3. So the square root of 4/9 would be equal to 2/3. It's kind of hard to show it, easier to show multiplication, but that is true. So let's take a look at some of these. So we have the square root of 10 over the square root of 49. Well, the square root of 10 can be factored into 5 times 2, but neither 5 nor 2 can be simplified into a square root. So we're just going to leave that as the square root of 10. But we can simplify the square root of 49. That is equal to 7. I could break this up also, but here's a hint. If you can look at that fraction and simplify that fraction before even dealing with a radical, most of the time that's best. So this can become the square root of 10 divided by 40 is the same as 1/4. And the square root of 1/4 is the same as the square root of 1 over the square root of 4. The square root of 1 is 1, and the square root of 4 is 2. So this is equal to 1/2. This last example, again, if you want to pause the video and try it, the square root of 5w squared all over the square root of 36. 5 is a prime number. It has no factors that are perfect squares, so that must stay under the radical. But the square root of w squared is w. We usually write the regular numbers out front and the radical after. And then on the bottom, the square root of 36 is 6. That would be your final answer. Okay, example 4 in your book is an application. The stopping distance is equal to the square root of 27 times the length of the skid marks. I can't remember what this problem did, but I would recommend that you look at example 4 in your book. Again, if you're finding the square root of a number in a real world problem, then you're going to want to go ahead and grab your calculator and find a decimal expression for that. All right, here's the homework. I will load this all on the classroom, and these problems will be due on Thursday. Thank you.